So, hello everybody. Today again we are going to discuss lecture number 13 in the series of fluid mechanics chapter 1. Okay, so I guess this one is the last lecture we are discussing for chapter 1. So I guess I have planned totally 13 lectures in this chapter. So the last lecture is basic flow analysis. Okay, the topic of the last lecture is basic flow analysis. Okay, so here I will quickly discuss some things, some important things. So how we will tackle some fluid problems, right? So and after this lecture we will maybe let's see, I will try to solve as much as many problem. I will try to discuss in the upcoming 2 or 3 lectures. Let's see how the plan goes. Okay, so now for current this lecture we are going to discuss about flow analysis. Okay, so whenever a fluid problem is given, so there are three three basic ways to attack a fluid problems. Okay, so they are equally important for a student whoever try to learn this subject. Okay, as everyone tries to adequate converse to each method, right? So it can each method is equally beneficial. Okay, so I will write the name of three methods that I'm going to discuss here. So the first one is control volume. Okay, control volume method. Okay, or we can call it as integral method. Okay, so many of you could understand from the word itself, integral method. In this method we will take, I mean we will take a packet of fluid where plenty of fluid particles will be there, and we will call it as an integral method. Okay, so we will integrate all the fluid particles and we will take whole as a one. Okay, so by this method we will study this in chapter 3. Okay, so currently I am discussing chapter 1. This is the last lecture of chapter 1. So in chapter 3 we will discuss this method, okay, control volume method or the integral method. Okay, and the second technique to study this program is we can call it by two name: infinitesimal system, or we can call it as differential method. Okay, so here in the above method we have discussed about integral method, right? We will combine all the fluid particles together. Okay, and in differential method we will study each particles as a one. Okay, and for this method we will discuss this in chapter 4. Okay, and the third method, third technique over which we are going to discuss is experimental study. Okay, experimental techniques, or we can call it as simply dimensional analysis. Okay, so we are not going to do experimental study. We are not going to do any experiment here for sure. So we are going to do dimensional analysis. Okay, so we will take pre-recorded data and then we will do dimensional analysis, and then we will analyze our problem. Okay, so this we are going to discuss in chapter 5. Okay, so I have planned these things accordingly. Okay, so I'm just telling you to prepare about these things. Okay, now, so all you can see there that all three are different methods, right? But for all three different methods, these are based on some fundamental problems or the laws. Okay, right? So this flow must satisfy some basic laws. Okay, this technique must satisfies basic law. Okay, so what are these basic law that we will discuss it here quickly. So some of the basic laws are, two mechanical equilibrium kind of thing. Okay, two mechanics law and a thermodynamic law, or okay, plus a one state relation is there, and another one is boundary condition. Okay, that we have discussed above, right? In no slip and slip condition. Okay, so what one is this? Two mechanical law. We will discuss here two basic mechanics, right? Mechanics law, what are these do? So these two are, first one is conservation of mass. okay, or we can, the equation which we are getting from this conserving of mass is known as continuity equation. Okay, continuity equation. Okay, and the second mechanics to in the two basic mechanics law, the second one is linear momentum, I mean conservation of momentum, or linear momentum law, we can simply call it linear momentum. Okay, or where from it's derived, it's derived from Newton's second law. Okay, Newton's second law. Okay, so whenever we are going to discuss any fluid problem, so first we will we will define these two law, we will solve for these two laws first, and then we will move forward to the second one, that is thermodynamic law. One thermodynamic law. Okay, thermodynamics law. And what is it? It is conservation of energy, or the first law of thermodynamics. Okay, so whenever we are going to deal with energy, we have to apply this this law. Okay, for any fluid problems to solve. Okay, so we can call it as a first law of thermodynamics. Okay, and the second the third one is state relation. Okay, this one is mainly for, this is for both fluid and solid, but no, sorry, both fluid, liquid and gaseous, but most probably we are going to use this for ideal gas equation kind of thing. Okay, so here density is a function of sorry, pressure and temperature. Okay, pressure and temperature. Okay, so this one is state relation law. Okay, and last one is boundary condition. Okay, okay, so boundary condition, we have we will choose it according to given problem. Okay, okay, some of the boundary conditions would be like no slip condition, or wall condition, no slip kind of thing. Okay, and then interface, inlet. Okay, some inlet would be there, some fluid is coming, and outlet, many kind of boundary condition would be provided here. Okay, so see, uh, so here we have discussed, you are going to listen these things again and again when we are going to solve this problem in the upcoming chapters. Okay, so please don't get confused there, and that means we are going to discuss each thing one by one. First we will discuss conservation of momentum, conservation of mass. Whenever we try to solve any problem in fluid dynamics, what we are going to do is we will first apply continued conservation of mass. Okay, for any of these three technique, we are going to use this. Okay, so we will first use the conservation of mass, we will get from there something, then we will use linear momentum, Newton's second law, and this will vary accordingly according to the program. Okay, and if some energy terms will be there, we will use thermodynamic law as well. For gaseous, we will use state relations, or we can use the table. Okay, for fluid, for liquids. Okay, and bonding condition will be accordingly will be chosen accordingly to physical condition of the problem. Okay, okay, so these are the things that we are going to do. These are the laws to be fundamental to physics, and no fluid is known to violate them. Okay, these are very fundamental laws. So for every fluid, these laws should have to satisfy. Okay, so yeah, so every fluid, every fluid should satisfy this law. Okay, so more or less we are going to deal with these conditions or this law only for solving any problem. Okay, so at that time don't get unconsciousness or like uneasiness whenever I take name of these things. Okay, just be aware of that we are going to discuss it here. Okay, I'm just making you easy. Whenever when we discuss this program, you will feel easy. Okay, at that time. Okay, so I'm just discussing here. So every fluid should follow these lines. Okay, okay, so this lecture is all about how we will going to discuss the how we will going to solve some problem. Okay, so I will tell you about why this picture I have taken here. Okay, so first I will just introduce the topic here. So yeah, this one is the second part of this lecture only. So in this lecture we will see how we will analyze any flow patterns. I mean, some flow will be there. Okay, so how will we analyze any pattern will be seen in the flow or not, or like anything. Okay, so the first thing is here is a streamline. Okay, I mean some method to find the to find the pattern in any fluids. Okay, so I mean, four methods of line pattern used to visualize flow. So any visually any flow is there, so we will use the four different methods. You can choose any one. I mean, these are the four typical methods, I mean basic methods that people are using to visualize the flow. You can choose any of one of them, or you can choose all of them, or you can choose any two, any three, any that depends on you and your program. Okay, and program. So I'm just going to discuss each method quickly here. Okay, so the first is streamline. Okay, so I mean it is a line. It is a line everywhere tangent to the velocity, tangent to the velocity vector at a given instant. Okay, so I mean this concept is instantaneous concept, right? We are going to discuss it at an instant, right? I have written here, right? I mean given instant. So see, any fluid is there. Okay, this fluid is moving here, right? And when we draw a tangent here at any instant, I mean this point, we will call it a t equal to t dash. I mean some point will be there. So this one is instantaneous quantity. I mean, yeah, so it will define at for a very less period of time the fluid. I mean we will draw a tangent to that velocity vector of the fluid. Okay, so that one is a streamline. Okay, this method is known as streamline. I mean when a flow is there, and you will see some pattern in the flow, and you will see the velocity vector, and you will draw a tangent accordingly. Okay, and then you will say that this is the streamline of the flow. Okay, so I mean a streamline is convenient to calculate mathematically. Okay, so that's why I mean I will write it here. Oh, sorry. Easy to equate or solve mathematically. Okay, but all other three, I mean path line, streak line, and another one is there, it is timeline. Okay, so all these three are, I mean, very easy to generate experimentally. Okay, that's why these other three methods are there. But this method streamline is basically for mathematical modeling only. Okay, so we will now see the path line. Okay, so in the path line we will trace actual path of fluid particles okay. So I mean see, when any flow is there, and you are going to trace particle of any given fluid particles. I mean you will just hold this particle, one of the particle. I mean many fluid flow is flowing, right? So there are many fluid particles will be there. So you will just hold on this to this particle, and you will just observe this particle, and you will see that how this fluid particle is moving. First one, it is here, second here, third position is here, there, right? And you will make a line. Okay, then that line is known as path line. Okay, so this method is known as path line method. Okay, and this is not non-instantaneous, right? We are observing over a period of time. Okay, non-instantaneous method, right? Okay, and I hope you understand these two methods. And now the third one is streak line method. Okay, in the streak line method, it is the locus of particles that have earlier passed through a prescribed point. Okay, so what does that means? You will, I mean, see, here in this case, you put a die here, right, and a flow is there. Here one model is there, I mean an obstacle is there in the path of the fluid. You will just hold on to this position and you will see that how many particles are passing over there, right, and you will make a locus of the particles, all the particles, and you will make a stick line, right, locus of the particles that are yearly passed through this point. So is, I mean, you will see that how many particles are passing through this point, and you will make I mean, you will take a data of all the fluid particles, and you will make a line, then that one is known as streak line. Okay, so see, this is also non-instantaneous I mean process. Okay, instantaneous method. Okay, so if you see, in this case we are focusing on, in the pathline method we are focusing on only one particle, right, on one particle. But here we are going to focus on one position. Okay, right, one position, and for one position many particles are passing, and we will draw the line accordingly to the particle. Here we will draw according to the position of the fixed particle, right. Okay, so this is the difference between the path line and streak line. Okay, and one more important point to note here is that streamlines, path lines, and streak lines are same for a steady flow. Okay, so whenever is a steady flow, we will say that both I mean all these three streamlines, path lines, and streak lines are same, right, for steady flow, right, because there is no turbulence. I mean, so see, if you observe any one particle or the many particle, you will get the same thing in case of I mean steady flow, right. There is no, I mean, no turbulence, and no, sorry, this is not about turbulence. I mean, there is no I mean, a steady should means it's flowing same manner over a time, right. So it doesn't matter whether it's instantaneous process or non instantaneous process, whether we are observing one particle or more than one particle. Okay, that's why all these things are same. Okay, okay, and the fourth method is known as timeline. Okay, so what we are going to do in this technique is to, it is a set of fluid particles that form a line at a given instant. Okay, okay, so in the other three methods you are observing for a I mean single particle, right. In both in all these three things, in a straight line, now we are just taking multiple particles at a time, but we are considering each particle at a time, right. So that's the case in the I mean previous three methods. In this case we are going to discuss we are going to think about all the particles collectively, right. So these are the different methods that we have discussed here. Okay, so some important point to note that a streamline and a timeline are instantaneous lines. Okay, while the path line and a streak lines are generated by the passage of time. That means non-instantaneous process. I have written here, right. So just think about it. And like streamlines are difficult to generate experimentally in unsteady flow unless one marks a great many particles and note their direction of motion during a very short time of interval. Okay, and in a steady flow where velocity varies only with the position, the situation simplifies greatly. Okay, that's why I've written streamlines, path lines, and streak lines are identically in a steady flow. Okay, so I hope you understand these methods. So from the next few 2 to 3 lectures we are going to discuss only problems, okay, regarding this first chapter. Okay, so many of you are waiting for that lecture only, that sessions, so we will discuss it there. Okay, till then keep learning and goodbye.